Hello everybody, you're very welcome into this video, which is now the ninth in this series of the investigations into the 2D airfoil for application to the front wing of a STEM racing competition car. In the last video we finished up on this screen, more or less, showing the table of design points and for leading into its usefulness within a parameter study. So the parameter study does show to the judges in STEM racing a level of iterative investigation into a steadily progressing and improving solution in this case, a computational fluid dynamic or a fluid dynamic, aerodynamic even problem. I was going to move on, obviously, into the mesh independent study in this, as I did say at the end of the last video. However, I did get a couple of emails in and people asking me about the table of design points and how that can be used, how to update it, what to look for, and so on. And I had a couple of questions there as well about the difference between the named expressions and the report definitions. Now, I think I'll take maybe 20 minutes or so and just make this kind of intermediary video to address some of them points and use that to do some preliminary work for the mesh independence study, which I definitely will do in the next video. And in that I'm using the grid convergence index method, and there's a couple of metrics that we need to set up for that. I think I could probably use this video to, number one, explain the report definitions and the named expressions with respect to creating these new metrics, which will help us in the later video. So I'll try to rationalize what's being done. Now, there is a slight difference with what you're looking at here versus what was in the last video, for the simple reason was that at the end of the last video, when I exited Fluent, I selected not to save set up for subsequent calculations when I should have. Momentary lapse of concentration in that, but anytime that you do set up named expressions or specifically report definitions, and you're going to do a parameterization study or parameter study using a table of design points, which will have subsequent calculations after your initial calculations without accessing the fluid application, um, you should definitely save your changes for subsequent calculations. I didn't do that. So when I went back in to make a change to a parameter, an AOA that I had instead of an A of A for angle of attack, although it was deleted out of Fluent, it kept showing up in my parameter table here. So what I had to do was I just exported this project and I imported it into a new project. When I did that there, it cleared it, but I had to redo Fluent again with all the messing that I had done on it to try to clear the AOA. So there'll be a couple of slight changes in it from what you had seen before, but other than that, everything is identical same. Now, one of the questions that kept coming through a couple of times was, why do I have a P1, P2, P3? And then why does it jump up to, for in this case here, P6, P7, P8, just to go back to P4? And can you reorganize these? Well, no, you can't reorganize these as far as I know. But what you will also see is white boxes here versus a kind of gray, shady beige box over to the right. And what this is the table of design points being organized into input parameters and output parameters. So all the input parameters are organized to the left-hand side, and then all the outputs are organized to the right. But then there's going to be arranged in their numerical orders, rising from P1 up to P8, which are all input parameters here, and then we go back to the P4. That's going all the way down to a P15 in this case for my output parameters. If my next parameter was parameter 16 and was an input, I would expect to see in column H a P16 and the name of the variable. Yes, the units can be changed where units are changeable, and obviously that's only going to be on the input parameters. So for instance, the angle of attack can be specified to be entered onto the table of design points in degrees or into radians. The reason I have selected degrees is that for the most part, we're going to specify our angles of attack in degrees. I don't think I've ever seen them specified in papers or in published experimental data or in textbooks. An angle of attack specified in radians. Degree, I think, is kind of the universal standard for that, so that's why that's in degree. And of course, meters per second there for velocity is fine. That can be millimeters per second or any other displacement per unit time as well. So moving swiftly on, if I move back into the project here, what I'm going to do is come back into Fluent. I'm going to click on to solution. It'll launch my Fluent window, and what we'll do is we'll tackle the named expressions versus the report definitions. So when I recreated Fluent, what I did was I created a lot of them back into report definitions as opposed to named expressions. I hadn't really planned on coming back and doing more kind of walkthrough videos on this. What I was going to do was go straight into the grid convergence index method and mesh. And what I did then was I moved things into the report definition, because what I wanted to do was to try to automate some of the grid convergence index creation of metrics to evaluate what is broadly a statistical method. But then when the questions came in about the difference between the named expressions and report definitions, when they should be used, when they shouldn't be used, and as well as that, my wanting to automate the grid convergence index method, I thought there this intermediate video might here just bridge that gap nicely. So the named expressions, this was fairly well populated in the last video. Angle of attack, velocity inlet, the cosine of the angle of attack and the sine of angle of attack. We also had our lift coefficient, our drag coefficient, our lift force and our drag force in that, I believe. And we had very little in the report definition, if anything. Now the named expression, what it does, it just gives you a final answer effectively for any of these. Everything I'm seeing here at the minute is an input in angle of attack and velocity input. Cosine of angle of attack and sine of angle of attack, they aren't inputs. Those are just calculations to give me a number based on an input. What I've done is I moved to my report definitions a lot of the output files. Now, I don't have to put them there. I had the output files in here, but what they would do if they're in a named expression is that give me a final answer, and that's it. And that's really all I expect to see when I look in my my parameter set is a final answer. For instance, my maximum Y plus, my maximum lift force, and so on. That's all I really want to see in that, because that's what I'm going to use, or a number of them, to measure my convergence and to validate my data against published experimental data and other publications. However, there might be cases there where I want to have values of them metrics on an iteration to iteration basis as my solution converges to final values for the metrics. If it's a case there that I want to have access on the running value of that over an iterative solution, I write that into a report definition. If it's a case I don't need a record of what's going on, I just write it in the named expression. So from a mesh convergence study, that's all really we're looking at our mesh independence study, apologies, and we're just looking at final values whenever a residual or whenever a an iterative error allowance or tolerance has been met. And we're only looking for the final answer. It's fine to do them in named expressions. I put these into report definitions, as I said, because it might be interesting to try to automate the grid convergence index method within ANSYS itself. You'll see many contributors that are doing the grid convergence index method will take the values out of ANSYS and they'll plant them into MATLAB or into Excel, and they'll do the calculations, the formula calculations in the external software, and then they'll output their findings from that method there. I'd like to bring some of that into Fluent, maybe take a step or two out of MATLAB or Excel, do that into Fluent. Maybe we can create a CSV file and export the whole lot then into MATLAB and automate that in a function to give me a final answer. But to do that, what I'd need to do is I'd need to have a reportable, reportable data. And for that, I need a report definition. So for that reason there, I've moved a lot of these into the report definitions. All right? I didn't have to move much of them, but I did. So yeah, let's go on ahead, and what we'll do is we'll set up a couple of parameters here now for the grid convergent index method for mesh independence. Now, what about this method here? Well, this method here was, I believe, penned by Roach, PJ Roach. Here it is here, 1994, I believe it was. Yeah, September 94, which it's based really on Richardson extrapolation, instead of interpolation, extrapolation. And the method and the thinking behind it is laid out in this document here. So I'll put a reference to this document in the comments if you're interested in reading up on it. It is good reading, but it's very hard to derive the steps on this. He does give a good example at the very end. And there's example, a reviewer has requested a simple example of the calculation of a grid convergence index. I choose the easily reproduced case of a steady state Borger's equation. Right, so there it is there. Okay, but to understand a lot of what's going on that, you need to have the document read first. So we don't have the time for that, and as well as that, for level 3 STEM racing, it could be, not that it's going to be tight, I have full confidence that you'll be able to do it, but what might be tight is the time. And there's a lot more to your project than aerodynamics and computational fluid dynamics. So, you can come back to this. At the minute, though, what you have here is CELIC procedure. Yes, this is a CELIC 2008, I think. Yeah, 2008, CELIC 2008, published online, not even in a document. Here it is here. Going up to the top, procedure for estimation and reporting of uncertainty due to discretization in CFD applications, 2008, CELIC et al. And what this is brilliant, let me just see, is published online. Right, published online. You can get this online again. I'll put a reference or link to this page in the comments. But this is absolutely phenomenal, because what it does is it gives a step 1, step 2, step 3. Step 4, step 5, and so on, all the way down to get down into the grid convergence index. All right, and then it gives analysis of them down here as well. Okay, so it's good. So this is the one we'll follow, kind of this one step by step. I think this is very handy, especially when it's laid out the way it is. So according to this, in step 1, we want to define a representative cell, mesh, or grid size. For example, for 3-dimensional calculations, we're going to use this one, but for 2-dimensional calculations, we're going to use this one here. So H is equal to 1 over N sigma between the first cell area up to the amount of number of cells you have of the area of that cell, and all that there is to the power of a half, which is a square root. So what I'm going to do, just to see, can we take this apart and see what's going on with it. Let's stick that on into OneNote here and see if we can understand how we can potentially code this. And so H is going to be, say, our characteristic cell size or element size. As H. N obviously is going to be the number of cells or elements in the discretized flow field. And then delta A is equal to your cell size, the area of your cell, area of a cell reference I, whatever it is, 1, 2, 3, 4, 5, all the way up to the amount of cells that you have. And that's all the terms in there, right? And then the power of a half. Now the sigma, we can see here that this is a discretized space, so obviously we're dealing with a sigma of the delta A as opposed to the integral of the delta A. Discretized, continuous. It was continuous until video 3 or 4 maybe, when we discretized it. So now we're dealing with this, but all we need to do is we need to sum up all them areas from I is equal to 1, my first cell, all the way up to I is equal to n, my last cell. Alright, so formula wise we can say that H, our characteristic cell size, this is all square rooted, so just in maybe more common notation, everybody might understand a wee bit better. It's going to be the square root of, I'm going to say A, total of A, over n, okay, just where A is equal to the total area of flow field. That's discretized, of course. 2D squared, it's area now, meters squared. Okay, so this is what I want to code here. Now, this isn't going to be outputted. Right? This is an output variable, but H is just one number for the entire mesh, so there's no point really writing that in a report definition. Right? So that's the thing. If that changed from iteration to iteration as I converge to the solution, yes, and you're interested in how it changed, definitely write it in a report definition, but there's no point me writing that in a report definition, because from the first iteration to the last iteration, H is going to be the same number, because A isn't going to change, N isn't going to change, and therefore the square root of A over N doesn't change. So that's something there that I'll probably write in a named expression. Now, A and N, however, are funny themselves. The area. What is the area of that mesh there? Okay, so the area of that mesh, or that discretized space, you would think you might check the surface of it, but it's not here in the surface. See this system flow field? And that isn't it. Interior system flow field does not give the size of that mesh, nor does system flow field. Those are going to return you values that are much larger than what you'd expect out of that. So for instance, if I did go to say named expression, and I hit a new named expression in this, and I wanted to write, I'm just going to do this generically because I'm not going to save it, but area, I'm going to open that up, and then I'm going to open up the brackets of where, let's see, locations, surfaces. If I looked at the interior system flow field, oh, I need to take off that double bracket, and I close that up. Didn't like that. It's not going to work it out there anyway for me. It's not given as having an area according to that. However, then if I look into report definitions, and I go to new surface report, and I look at an area, right, and I look at the interior system flow field, and I compute, I get an area of 541. You see it here in the console. It's huge, much too big. There's no way that the area of my flow field, the surface of my flow field, the face of it is that big. And that's generally looking at the cell areas, the faces of the cells. Similarly there, if I go to system flow field and hit compute, 2.34, slightly better, but it's still too large, given that, if you recall, the diameter of this here is 0.75 meters. We're running back here 2 meters by obviously 1.5 meters, so we're probably in the region of 0.57, 0.58, maybe a wee bit more, maybe up to 6, but we're in that region. We're not near 2.3489, let alone 541. Okay, so that's not what I'm looking to. So I can't see that there. See that area, these systems and these flow field and whatnot. It's not working the way I want them to do. So what I want to do here is I want to create a new surface and take the area of it, a surface there that actually is correct. Okay, so if I cancel on out of that and I come down, I'll actually come over here to surfaces. So in domain, surface over on the far right, I'm going to create a zone, right? So I'm going to create a surface from a zone surface. Now, solid system flow field, you see solid, that's just the way I left it named whenever that fill command was applied to the sketch that I made in Discovery at the start when I first made my 2D surface. Solid was defaulted by writing that. It's not solid. It's meant to be a fluid and it's specified as air influent, but nevertheless, that's just the name of it. That is my discretized domain. That's what I created there. So the solid flow field. So what I'm going to call this one here is going to be, say, discretized area. Okay, discretized area. I'm going to create that, and there it is there now. So there's surfaces. I now have 6 surfaces, discretized area down to these. Now, I would like to create that in named expression, but it won't see it in named expression, unfortunately. So I can go to new. I look at locations, boundary and surfaces. It's not there. It's still only 5 there. Why is that? Well, because this is retrospectively made. All right, Fluent knows nothing about this. It's not going to pull it up like that. The named expression, I think, takes very surface sort of ideas, and you write what you're looking for specifically. I would rather write this in here as a named expression and not have to write it into report definition. But report definitions kind of give me a lot more derived quantities or access to derived quantities. So I'm going to have to, in this case here, omit writing out the named expression there. I'm going to go to report definition. I'm going to click a new definition, surface report and area. But this time here, look, discretized area is now available because I created that surface. Even though I retrospectively created that after, it's available there. Now, definitely no report file, definitely no report. Again, definitely, I don't want an output parameter here. I'm not really interested in what it is. It is what it is. Okay, so what are we going to put in here? We'll just call this area of the discretized flow. I'll keep the dot out of that and put an underscore. Flow field. Don't really trust dots in Fluent. Area, a discretized disk flow field. Okay, discretized area. If I compute there now, 0.595, that's what I thought it was. I thought it was maybe around 0.7, 0.8, maybe up to 6. It wasn't that far off, but yeah, I'd be fairly comfortable with what that is. In fact, it could have been about 0.6, but by the time you take out the void where the NACA 0009 airfoil was, it could have brought it back down to that. So there's my discretized area, nothing else to do with it, no reports files, that's it all. Okay. In fact, you could have made a new surface in report definition instead of going up here to do it. Okay, so looking at our formula here, I now have my area. Now the number of cells that I have in this. Now there's a couple of ways of doing the number of cells in this. The first thing to bear in mind is that we know what the number of cells is. There they are there. That was in my table, 165,600 cells there. And you would think that I should just be able to pull that from somewhere, obviously, like a named expression. In fact, if I look up here in domain, and I look at the mesh and I look at info and HG size, I can see it there, 165,600. Now, the thing about that is to access that data as well, I have to do another report definition, which I don't want to do here if I can. What we can do is a mesh report cell count. Click where I want it in the solid system flow field again, which is not my discretized, not my surface that I created, but again the zone, and I hit compute. And there we could see there 165,600. Now I can do the exact same thing, name that cell count, blah blah blah, but it's create another report definition. Not that it's any harm, it's not that different from a named expression whenever I take off my report file and my report plot. But what I'm going to do is I'm going to make this in a named expression, or try to, by using expressions, just to show that it can be done this way as well for some things. So what I'm going to do in this one here is I'm going to go for new named expression. I'm going to call this cell count. Right? I don't want this to show up anywhere. I'm just using this as an expression to calculate something else. And cell count. So what I want to do is I want to take a sum here with capital S. Sum of what? Well, the sum count for me 1. Put a 1. Sum up all the ones that are in a location, which is going to be a cell zone in the system flow field location. Now, I need to put that in a square bracket because it is a location. Close that bracket. Right, let's refresh it, and there's 165,600. So there's my cell count. Input, output parameter. Nah, don't need it there because I'm already outputting that from ANSYS meshing into my design table. So I don't need to output it again. So now I have cell count in there. So now I have all the tools. I have everything I need to calculate my characteristic cell size, H. All right. Report definition. Now I'm going to put this in as named expression as well, and then assign that as an output parameter because it doesn't change from iteration to iteration. So the area was the only thing I had to write into the report definition there. So I'm going to create a new one here, right? And I call this characteristic cell size. A wee bit long for a parameter name, so what I might just do is take that down to char. And what I want to do is put a hyphen H in it, just that I'm going to recognize it as a H. It won't let me do that. I can put in a hyphen in report definitions. Can't put it in the named expressions. So this one here is going to be the square root. All right, so that's a small s for that one, where sum was a large S. The square root of the area. So the area is a report definition. So there's the area of the discretized flow field that I created there. Right. Divided up by the number of cells. The number of cells was an expression, cell count. Right. That should be it. Now when I let me just write a description. I'll show you how the description there work as well, or where they come in, very handy. This is going to be the characteristic cell size of I don't even have the right current of discretized flow field. Right, step 1 of grid convergence index method. Lovely. Put that as an output parameter because I want to report that. I want to see what it is. All right. There is an argument that I probably could put that into the report definition if I wanted to pull that data out. Yeah, probably would be better. Tell you what I'm going to do. I'm going to cancel that. I'm going to write that in as a report definition now that I think of it. Surface report expression. So again, same sort of interface. Again, why am I putting it into the report definition? Well, if I'm going to automate this, I'm going to get a H size for this mesh. I'm going to get a H for another mesh. I'm going to get a H for another mesh. I want to be able to pull that data out of an external file, where if it's written in a named expression, it's not in an external file. It's just blurted out as a result. If I'm only going to lift the number out of the parameter study, out of the design point table, just read it and copy it out, yeah, keep it as a named expression. But where I might want to reference a CSV file or reference a particular file in the likes of MATLAB to pull out this data and then automate a calculation, I'd have to write it out in a report definition. So what I will do, I'm not going to bother reporting the plot, but I will write a report file, and I am definitely going to create an output parameter for it. So we'll keep this the same as characteristic cell size, and then there's the hyphen is allowed in the report definition. So again, this is going to be the square root, exact same syntax, square root. We're going for another report definition we had, the area of the discretized flow field divided up by the expression, the cell count, close bracket, and compute that output parameter, report file. Don't want to print the console, no need, report file. So there we are. And we're down to meter squared and to the power of a half, characteristic cell size 0.0018968711. Okay, that's it. See, workbench flashing away here for some reason. All is okay. I'll give her a second there to come through. See what happened there. Unexpected error while refreshing pane. Maybe hopefully it is just a reflection when it outputted the parameter to the pane. Maybe it just did not want to put it in. Drag force, pressure output, Reynolds coefficient. It just hasn't put it out there. Let's see how we go here anyway. Let's make sure it was created. Characteristic cell size H. Output parameters created. Compute. We're good. Okay. Closed. Alright. Let's see how it goes. Alright, so now when I exit this, it's going to say, do you really want to close Fluent? I'll say yes, and then this again, okay, settings have changed. The settings have changed. How do you like to proceed? Because I have done work on not so much named expression, but more so report definitions, and that I'll say here, use settings changes for current and future calculations, because that helps me with the design table. But as a matter of fact, what I'm going to do, I'm going to come back to that in 1 second. I just want to check in my solution here. My methods again should be in coupled still. They are coupled. I did find a paper here which promoted using simple C. I would normally default myself this. I was it there. Procedure for estimation, reporting, uncertainty due. No, that's not it. Sorry. Numerical investigation, transition flow around an NFL airfoil. So I had a good read down to this one here. It's one that I came through now. It is 3D, but again, it's roughly the same Reynolds number, same sort of ideas. Simple C was proposed in this one, so there that the coupled used unnecessary computational power to solve. So if you are getting it tight with coupled on your machine, definitely try a simple C. Do not try piezo. Don't need piezo for these sort of flow applications. So laminar. Simple probably work. Simple C is a wee bit better, I think. I'm going to stay with coupled anyway for it. And then what I'm going to do as well is in my calculation, 500 iterations. I've been fairly happy with that. I'm going to throw this up to 800, throw it up to 600 iterations. Again, I'm doing things in sixes now. And I'm not going to calculate it here, right? But I'm going to calculate it outside. All right. Make sure that's up brave and high whenever you're doing a table of design points in a parameter study, because it's not going to tell you has the solution converged out in the table. So you want to give it plenty there to make sure that it has converged. Because you could look at the data on the table, and some of it there just mightn't make sense. Some of the numbers could be a wee bit off, where you might be expecting, which we'll look at now here in a second, as the angle of attack increases, we should be seeing higher lift forces, and we should also be seeing higher drag forces. But what if you've seen a lower drag force? Well, if you've seen a lower drag force, you're probably your first place to look at is that have you given it enough iterations there to allow it to converge. Maybe it just went high for a wee while, went the other way for a wee while, and it just stayed there for a period of time, and then it stopped after a couple of successive convergence values there. So yeah, give plenty of iterations, and what that means to do what I'm going to do, I'm going to pause the video and go to sleep. It's the middle of the night. Get up in the morning then and have a look at your results. Okay, so let's X out of it now that I know that I'm on 600. X that out, quit, and then use the settings. Make sure you select that one. Okay, if you're going to work on do a parameter study and work on the table of design points, make sure you select that one. Okay, because if you don't, it'll work for the first one, this one here that you're retaining the data of, that you're saving on, but all subsequent design points there, it's not likely to work on. It'll revert back to other expressions. Now, I've added in more outputs, so they have changed. But what I'm going to do here, just to show how the table design points works, and hopefully to satisfy some of the other queries that came in or answer them, is that I'm going to change an input parameter and rerun all these design points and read the output parameters. So what we'll do is I'm going to go back to Winslow here, which it's a good clear paper. And in Winslow, if we look at, say, pressure coefficient, we'll do it for each of them. Do it for pressure coefficient. We'll also do it here for our lift and our drag coefficients. But in the first part here, our pressure coefficient table, there's a pressure coefficient measured here for angle of attack is 0, 2 degrees, 3 degrees, and 5 degrees. So I would propose there that I put in angle of attack of 2 degrees, 3 degrees, and 5 degrees, run the calculations, see what my minimum pressure coefficient is going to be. Right, the minimum pressure coefficient is going to be. So that might just have to change that. Make sure it is reading minimum. Minimum pressure coefficient is going to be, and compare to this data and to see does it work. Hopefully it does. So that is, apologies, 2, 3, and 5, 0, 2, 3, and 5. Down here, what's measured? Angle of attack 2, 4. Let's try 4. So let's do 2, 3, 4, 5, and 6. 2 to 6 we'll try. So that's a lot of calculations, different angles of attack. But if they are all thereabouts, we'll measure lift coefficients and whatnot against these drag coefficients. If they're all thereabouts, we know we're on to something here. We're on to the winner. So what I'm going to do, I'm sorry, I'm going to go back into solution. Yeah, go ahead. And what I want to do is I want to check to make sure that my pressure coefficient is reading the minimum facet data as opposed to the maximum facet data. I just want to double check that I just have something itching at the back of my head that it is max, and that could have been something that I just picked up, noticed in the parameter set. Max y plus, maybe let's check the Reynolds number pressure coefficient. Maybe I'm just imagining it, but better safe than sorry. All right, it's coming through here. There we go. Right, so this was that was report definition. Drag coefficient, pressure coefficient is there, and we are checking facet maximum. There you are. I want to do facet minimum. Okay, that's it. Yes. Now we haven't added in a new report definition or named expression there, so we weren't asked to confirm if we wanted to save the settings the second time. So we'll let that close off. We'll set up the additional design points based off of angle of attack to match Winslow's paper here, and because Winslow has experimental data in it as well. It'll be phenomenal for us to check our work against that. So this is how the table works. So I can change my amount of divisions, my mesh, my velocity, and my angle of attack. Those are the parameters, my input parameters now that I've left that I can change. So I'm going to just change angle of attack. I'm going to leave my meshing as it is. We're going to run this, see does the results corroborate with the experimental data. Let me just hit save on that just in case it crashes overnight. Parameter 16 not found. There's P16. That there is obviously my characteristic cell size. We'll have to come back and check that, but I'm on to nearly 40 minutes, so I want to get this bit done. I'm going to do 2, 3, 4, 5, and 6. Right? Different angles of attack. I'm going to run this. Right? It's going to calculate all these new values here for me. Q back out. Alright, I'm just slightly put off here that I don't see piece 16 on that, because I would have liked to have seen that one come out. Oh, there it is there. It did come out, P16, the characteristic cell H. So we'll be able to read that there for each of these. So this one shouldn't change because we haven't changed any of our mesh divisions. The only thing we should see changing in this will be our Y plus, because our friction wall velocity will change, our wall friction velocity will change. Our lift force will change, lift coefficient. The Reynolds number shouldn't change. That's based on the inlet velocity. Drag coefficient will change, drag force will change, and the pressure, the minimum pressure coefficient will change. Okay, so when you get that done, you can run any of these here separately by right-clicking and update the selected one. If you want to retain any of these here, you want to retain the values on them, write them into the file. You click which ones you want, and then this one, you can also select the current one there. Say if I wanted that one, you can create that to be the current one, but it has to be solved first. I'm just going to leave it on that, and then up here, update all design points. And then when I update all design points, then we're going to kick off a calculation. It's going to start with design point 0 and work its way up to design point 5. So there is 6 of them here to do, and I'm going to let that walk away. So at 41 minutes, this could take 600 iterations. It's all steady state solver, so there's no time stepping, and it could be a wee bit quicker. But that said, like 2.5 hours, I would still expect. So what I'm going to do is I'll pause this. I'll tell you, I'll actually stop this just in case the thing crashes. So I'm going to stop this video, and then I'll make another intermediate video just to show you the results. Hopefully everything went okay, and yeah, see how it goes. We'll compare that to Winslow, and then eventually we'll get into the mesh independent study. Okay, so thanks very much, and I hope this clarified a lot of the questions that arose out of the last video. All right, thanks very much.